Okay. What were we talking about? You remember? Looking in the notes. Something with the stuff, Coriolis force. Yeah. Yeah, so there's a technique that we haven't yet talked about in detail, which is creating dimensionless numbers. Are you familiar with this idea? So this is a way that we can look at a complex problem, such as the fluid dynamics equations, and figure out when certain terms are important. So if, for example, let's go back a few slides here. Whoops. Okay. So let's have a look at this this equation. Okay. So this one here has a lot of terms. Yes. Right? And we're saying to ourselves, okay, how do I know which terms that I need to consider for a specific set of circumstances? That is to say, I'm thinking about flows that are on a geophysical scale, that is to say, comparable to fractions of the Earth's circumference, compared to those that may be occurring, say, in the classroom. So if I have a laboratory demonstration, do I have to care about the Coriolis force? If I have a hurricane, do I need to consider the effects of, say, pressure differences or gravity differences? So we have a complex equation like this, and we can use a tool called dimensionless numbers, and we can take ratios. Okay. So one ratio that I want you to learn about, and we're going to introduce different ones over the next 2 weeks. This one is called the Reynolds number. And we denote it with RE. Okay. So the Reynolds number takes a characteristic velocity and a characteristic distance, okay, divided by 2. And then it divides it by the viscosity. Okay. So how did I get that? What the hell am I talking about? Well, in practice, what we care about here is the Reynolds number really means U times D. Is that a property that we know? Not really. But there is something like U, and this nu, that's coming from these types of terms, the viscosity type terms. And if I look at how this thing is constructed, this is like viscosity, let's call it nu. And then this thing is dx, right? Something like that. And then this part is dx u, right? So really the units of this section here is like nu over d, right? Okay. If I break this thing apart, it looks like this, right? This is the effective term. So I can write this thing here as not only this, but also u dx of u, something like that. All of this times rho. Does that make sense? Okay, so this is the advective term. And it kind of looks like u times b dx of u. this is the diffusion or the viscosity term, and it kind of looks like something like the viscosity divided by length times v dx of u. Right? So we can say to ourselves, what happens if I take the advective term and I divide it by the viscous term? Well, you get the Reynolds number. So what if the advective term is much, much bigger than the viscous term? What does that mean? Okay, I should have taught you about this in chapter 1. Dimensions. This is the first time we talk about dimensions. 62. Yeah. So if you go to page 164, 162, 160, basically all through 169, 411 is dimensionless forms and the equations of dynamic similarity. And what it does is it basically compares different terms. And we can say to ourselves, okay, what does the fluid look like if one term is larger than the other, generally speaking? So if the advective term is more important than the viscous term, what are you likely to have?
Turbulence.
What?
Turbulence.
Why turbulence?
Just thinking like if I have the low viscosity and I'm adding something to it, it's like I would say like it's moving really fast. Versus like if I'm adding something and it's high viscosity, the honey, like I'm just thinking like water and honey, like a honey would not move as quickly if I'm adding an advective term to it compared to water.
Okay, so I think because we haven't really studied turbulence in detail yet, especially how it works on boundary layers, I'm just gonna change that statement slightly, right? We haven't studied the idea of laminar flow, so we don't know what turbulent flow is. We know what viscosity is, right? What this means is that an advectively strong object compared to the viscosity, this means that the advective terms are more important. This means that it may in fact be laminar, right? There is no guarantee here that this isn't laminar. Just because the viscosity is low, that means that this term here is low. And so the equations might look inviscid, right? That's all we know so far. Once we fold in the idea of whether or not they are in fact stacked together and whether or not there's any sort of motion between them, whether there are eddies, whether there are any turbulence, then we can come back to this and think about what these numbers mean in practice. Because I'll give you a hint. The Reynolds number is not greater than or less than 1 gives you two different phenomena. It's a scale, and the scale varies dramatically, right? Because these two numbers are not one over the other. Is that okay? So we can in fact do that with all of these different terms. And if you go into the chapter 4.11, you see things like the unsteady acceleration versus the advective acceleration. So that would be something like this first term here, the unsteady component, compared to the advective component, right? Or I should be more specific. This is the unsteady acceleration here. And this is the advective. So you can take the ratio of those, and that's called the Strauss number. You have heard of one. And this one describes planes going real fast. What is that called?
Sorry, say that again.
Planes going real fast.
Like airplane flying fast.
If you've ever grew up thinking about planes, fighter jets, you thought about this number? This is the Mach number.
I was thinking Mach speed.
Yeah, so what does Mach number mean? Well, the Mach number is really, it's a ratio of the inertial force compared to the compressibility force. Okay? So this is talking about something that's not just here in this term, this is not the full equations, but this is talking about our ability to compress the fluid. And if you write it out, it looks like this before we do it. So I'm going to do something like rho u squared over L divided by rho c squared over L. In order to get these dimensions to work out, we do something like this. But if you look sort of carefully at that, you see the rows are top and bottom. The terms are quite similar when you write them out the first time. And so you end up with something like U divided by C. And this is the Mach number. And this is a comparison, again, of the inertial force to the compressibility. I'm giving you just a small introduction to this because we're going to use this when we want to talk about geophysical fluids. Okay. In this particular circumstance, you've heard this before. This is how much faster or slower you're going than the sound speed, so to speak. It's kind of a misnomer, of course, because the sound speed depends on where you are in the fluid, right? It's not just the sound speed at the surface, right? It's throughout the air, right? As you move up, the ability for waves to travel changes because the temperature is changing, the pressure is changing, and therefore the sound speed is changing, right? So we don't just think of it as the 343 meters per second down here at the ground. Okay. And of course, U over C getting close to or near 1 means that your object is moving so quickly that the ability to send information is getting compromised because the inertial forces are greater than the compressibility forces, and the way that information travels in fluids is through waves, wave fronts and wave propagation, right? As to propagate through the media. Once you approach or pass 1 for the Mach number, you are now in a place called jumps or discontinuities or shocks. And so you need a way of tying those fluids together. Because in fact, they happen in nature quite frequently. It's not like going faster than the speed of light. So we do have mathematics to describe that. And I believe that's in chapter 50 or 60. Okay.
What is it? What does it mean to go Mach? Never heard Mach.
You're going the sound speed.
Okay.
Yeah. So as you go the sound speed, okay, So let's say you're going a little bit less than the sound speed, and let's say you have a plane. Don't look at my plane, okay? Alright, that's a good plane. That's actually a great plane. Stop, it's a great plane. Okay, so it's going fast. Let's say it's going V equals 0.9 C. So air, from its perspective, it's not moving. Right? So from its perspective, flow comes in, right? And on the surface of the plane, the velocity of the flow has to go to zero identically. It's a continuous object, right? So you build up basically a little layer here of zero flow. And then it needs to smoothly go from zero off to whatever the speed is. So if I look, say here, and let's say this is my vertical, okay? I have some high number that needs to go down to zero. And this is, let's assume that down to zero here. And here's some big number u, right? And this is some h away from the plane, right? And this is v, right? And so you get a little buffer. And what happens around this plane is you get little ripples of compressed air. It pushes the air up and it sort of deflects the flow. So instead of coming in straight, now the outer streamlines, they are bending around that compressed flow. Right? Okay. Let's go to sound speed. Now the ability to create this boundary is starting to break down. Why is that? Well, you are going faster than the compressibility force can accommodate. So instead of this going around you, it has no information that it needs to turn and just smashes directly into you. And it creates a cone that we call shock. So something's traveling with that. We get a 45-degree angle where flow just impacts it.
So is that what you see like on fighter jets when they take out there?
No, they're not going Mach 1 yet. That is a condensation cone. That occurs due to the fact that, yeah, you're shocking the air and you can get condensation from that. But the shape of the cone, regardless of whether or not you see the condensation, is there. We just don't see the air until there's something in it. But if you look for a video of a plane going Mach 1 and they're going through it, you may or may not see this, right? Like this. But if you look at, say, a blackbird or something that's traveling the upper atmosphere, usually they'll light them from below. Let's take an image from below. And what is really cool that you'll see distortion in the air. So you will see ripples behind it that are not from condensation, but from the fact that, just like when you're looking through, say, a glass that's distorted and the spoon or the straw breaks in two, that's what's happening due to that jump. You're literally getting a separation in the air. And so the background that you see through it looks wrong.
Now, this is just like a little thought that I was thinking.
Yeah.
Is it that the plane, because I don't know the answer to this, but I'm thinking that the planes do travel faster than 343 miles per hour.
It's not miles per hour, it's
Meters per second.
Yeah.
I'm thinking, never mind.
Yeah.
I was like, when you're in cruising altitude, pretty sure you're going like really fast.
Yeah, you go 700 miles an hour.
Yeah, and you don't like.
You don't even close to approach this sound speed.
Okay.
So the reason why you're not even close to approaching the sound speed is because sound speed went down.
Yeah.
Oh, sorry. The sound speed went up because
it's less dense up there.
Right, and it's colder.
Okay.
Right, so sometimes those work against one another. So usually, colder means that higher density, usually. But since we're going up and the density is going down, right, there's a combination of those two factors. Right?
So would it be easier to go at the sound speed the closer you are to the surface?
No, because then you're running into more air. The reason that planes fly up in that altitude is because there's less air. And there's less turbulence, there's less drag. You want to maximize your plane's fuel efficiency. So it's easier to fly at 30,000 feet.
No, I know that, but is it easier to approach the sound barrier at higher altitudes or lower altitude?
What do you mean by easy?
Like me as if I'm a fighter pilot, would I rather go 343 meters per second like down here on the surface, or is it I'll never sense wrong.
Take it. All right, good. I didn't need to do it. That's perfect. Internalized it. Okay. So now let's talk about geostrophic flow. So in order to talk about geostrophic flow, we have to make some decisions about what's important to us. Okay. So we could consider these equations of motions, and we could say, hey, I want to look at flows that are quasi-static. So let's do this one pretty much equal to 0. Now I'm going to be a little fucked up here, right? I'm going to say kind of static. Because we can do all of our equations, right? We can take our density and we can say there's some average density plus some perturbation, right? This is the perturbation theory we were thinking about earlier. And we can look and we can say, okay, here's the Earth, but if I look closely enough, it's mostly flat, right? If I go stand near the surface, it's mostly flat, and there is some vertical components here, but it's mostly like layers like this, right? So we ask for like horizontal variations that are stronger than the vertical variations. We just saw that when we were thinking about internally stratified media, right? So we're going to ask for some of those things. We want to look, say, in the atmosphere or the ocean. We want to be away from the boundaries. We don't want to have to deal with the boundary conditions, right? Messing up our solutions. So let's go ahead and write some. And you're going to see why I did these numbers in a few seconds. I promise this wasn't just me being bored. Okay. I need a button that I can press that does this while I'm talking. Maybe I need to learn how to talk and do this while not looking at me. But I love looking at you. I can see whether or not you understand it. Okay. So here's the first thing. We can write the Coriolis acceleration. Okay, and we can say, in what circumstances does the Coriolis acceleration match the horizontal pressure gradient acceleration? So we can write down our equations and we say something like this. F V. Now what's F again? When we're talking about Coriolis, what's F? What's the Coriolis parameter?
So the equation omega for -2 p cos cos u, or was it in the?
It's just this.
Oh.
Yeah, it might be that other thing too, but with the cross in there, I don't know. Yeah, I can never do cross products in my head. And this one's easy to remember. So the thing that's interesting about the Coriolis parameter, okay, is it takes some of the guesswork out of the Coriolis term. As long as you're on Earth, right? This thing is 24 hours per day. so to speak. And this is your latitude, sine of your latitude, right? So that just gives you a very easy F calculation. And as long as your latitude's not changing too much in the problem, you could probably treat F as a constant. Right? This is certainly a constant. Right? Okay. So we can set this thing equal to minus 1 over rho naught dp dx. Okay. We can think about this in terms of the linearized equations. Okay, there's going to be small perturbations to the pressure. So if you want, you can use this. For me, I'm just going to use prime. So that's one of them. This is the balance of the Coriolis term versus the pressure gradient. And then this is my favorite one. Okay, minus 1 over rho naught dp prime dy. Okay. So what have we said? Okay, let me show you again. Here's the Navier-Stokes equation. Okay. On the left-hand side, we said this thing, basically 0. Let's get rid of it. This one, we're going to keep. This thing, we're only looking left and right. We're not looking up and down. So let's ignore that one. This one doesn't exist at Earth, because the Earth is, we're not moving relative to anything in our frame. This is our Coriolis term, so let's hold on to that. This thing, we're not changing the acceleration of the Earth, so we can ignore that. This one here, centripetal acceleration, that really only affects what is the centripetal acceleration mostly do? Yeah. So what do we take this term and turn it into? Modified G, right? If I'm at the equator, I weigh less than if I go to the North Pole. And that's not just because I'm wearing more close to the North Pole, right? It's because you're getting flung off. So this is basically a modified acceleration term. And we said, okay, we don't really care about the viscous effects here. So let's create a balance then between Coriolis terms and pressure terms. And I can see now, okay, this is the minus dp. And I just take this thing and I put it on the other side. And then I divide by rho. And that's how I get these two terms. This is my x component. This is my y component. Okay. So do I see any flows where the Coriolis term balances any pressure gradients? Because this would be a little weird, right? Like, what would that even look like? Well, if you look at a large enough scale, okay, and I have a high pressure zone over here and a low pressure zone over here, what should happen? High pressure, low pressure. Well, just, okay, in a normal day, high pressure here, low pressure here, what happens? Yeah, but I mean, like, let's say I'm a piece of wind, or I'm an airplane or bird.
Harder to fly.
Good, and let's say I'm traveling with the wind, like I'm a leaf blowing in the wind. Yeah, so I go from here this way, right?
Yeah.
Okay. So let's work that out. Okay. Here's H. Here's L. Okay. And I go from this way to this way. Right? Okay. Let's say we're in the northern hemisphere. Okay. Now let's say I want to go from H to L, but I'm on Earth. And let's say this is a sizable distance in the atmosphere, or maybe in the ocean. Okay. Now what happens?
If you're going up north or
No. So I want to go from H to L. I want to go from high to low. I have some pressure that's pushing me to go from high to low. And I'm just a bird or a solar surfer, something that doesn't have a lot of choice. I guess a bird would have some decisions. Let's say I'm a leaf and I'm getting blown by the wind. I'm super high up. Get blown by the wind. Okay. Where do I go? I just follow that same path if I'm on Earth. Big ocean.
Go up or down, try to decide which way. You go.
Ah, why would you go up or down? What's the trick here?
To say it's a longer path, like going down. I feel like it's a less path going up. Because
You're thinking of great circles. I'm thinking about forces. So you're absolutely correct, right? If I take a curved surface and I draw a line across it that's straight, it's gonna look curved, right? Well, that's not what I'm talking about yet.
well, gravity's gonna bring it down.
So let's imagine that we're looking down on this, okay? So you, the observer, are looking down, and I deleted the picture earlier. Basically, here's the rules. We're on Earth. It's horizontally different. And mostly I don't care about the vertical. Okay, so it's like varying, like we saw sort of uniformly. Okay, and maybe there's waves going out. But I'm mostly caring just what happens left right. And what I want to do here is I want to balance Coriolis terms with the pressure forces. So what does Coriolis do in the northern hemisphere? What is the effect of the Coriolis force? If I take a ball, phone, I don't have a ball, and I throw it at Zori, who catches it? Now, this is not the right configuration because you're both behind Zori. Let's say Zori was in the back of the class and I throw my phone at her, who catches it? What? Yeah, okay, good. Unless I throw really bad. But if we were on a merry-go-round,
Oh,
right. So as the frame rotates, throwing straight doesn't go straight. So if we're on Earth, point A, does this thing go from high to low? It can't, right? So what happens as it tries to go from high to low? Which way is it deflected?
so,
How confident are you?
if I'm at the top, I'm looking down at the top and I see somebody throwing it flungs out, like if I'm at the north and I see somebody throw a ball, it flungs out not towards me, it goes the opposite direction. So I'm gonna go south.
Okay, so let's think about what the force is. Okay, not this one. Right, that's the centrifugal acceleration. It's this one. If you're at the North Pole, okay, that's this crossed into the velocity, which can only be this way. So your force is necessarily that way. I can do this the other hand better. So it's up at the North Pole. If I throw it in any direction, right, maybe this way, this is always going to make it turn
Towards. Or if you're at the north, it's gonna make you turn towards you. What you're saying?
No, so I'm here, right? The rotation is going through my body. I throw the ball this way. Which way does the ball go? Yeah, to the left, right? You see that?
So then control this.
So now let's try the equator. Okay. So the equator, it's still up. But now all of the motion, right, is in the same plane. So if I go up, there's no Coriolis. But if I go left, yeah, which direction?
What
Let me draw the picture again.
do you mean, which one?
So here, look. Right? So here's the rotation. Okay, planet. Here's omega in the north. Right? It's very easy to see when you're here that you can induce motions in 3 dimensions, right? The thing is fully rotating, and as I throw a ball this way, it's going to deflect up or over, right, depending on the angle. But let's say I go this way. There's a complicated cross product here. Right? Because here is my coordinate system. Let's say that's, how did I do this? X, Y, Z, right, like that. And I need to think about them with respect to the north, right? So in this system here, right? Oops, where'd I go? In this system here, I'm thinking about the rotation of the Earth crossed with the velocity vector, 3-dimensional velocity vector. So there is going to be some component of omega in each of the 3 u directions in my transferred, right, that my rotated and rotating coordinate system. Okay. Yes or no? At a specific location in the northern hemisphere, okay, we have Coriolis terms that look like this and like this. Now let's have a look at what this meant. 2 omega sine theta, right? And they depend on whether or not there's any velocity, right? So v and u, the x component of the velocity and the u component of the velocity, they're going to have different signs, they're going to have different directions, right? Because these are essentially how your velocity is going to change as a function of time, right? Okay. So in this circumstance, H in the northern hemisphere actually has a Coriolis force, which is balanced against the pressure force. Okay, that's how we wrote this. Coriolis term balanced against the pressure term. So there might be a horizontal pressure gradient, dP dx. But it's got to be balanced with the Coriolis term, meaning it has to rotate. Has to keep going around in a circle. Okay? So you want to go from H to L, but instead, go like this. Oh, that's the right. I can draw a similar circle around L. Yeah. How's this flow going? It wants to go into L.
Wants to-
It really wants to go this way. But it can't because the surface is rotating. So this one, maybe counterintuitively, rotates counterclockwise. So you're saying to yourself, well, that seems stupid and it seems impossible, right? Well, then you just have circles like this. And what? Like circles like this. You have a high pressure over here and a low pressure over here. But rather than ever making it from the high pressure to low pressure, you go in like this and you turn. In the northern hemisphere, from the high pressure, as you leave the high pressure, you're rotating to the right. And this one, as you're heading toward the low pressure, you're heading towards the right. Okay. This one curves you around. This one curves you around. Okay. Do we see these in practice? What? It's not quite a hurricane, but you're getting close. So this is the picture. Wait, here we go. Oh, it already was there. Okay. This is a balance of the pressure forces and the, yeah, I'm not gonna cover it up.
So like, do they like never interact?
Well, remember that this is. Work. Let's go. Okay, that's a great question. Yeah, does air ever go from high to low? Yes. Why?
I don't know, it's constantly changing, I mean, there's no way. And there's such thing as like turbulence, and then there's response.
This is a first order motion. You said something really important. And we talked about it a little bit earlier today, turbulence. We haven't quite talked about what it is, but we have an intuitive feeling of, yeah, it's a little bit more complicated than what you're saying, Dr. Bismay, right? So what we just did is geostrophic balance. We made a claim that Coriolis forces and pressure forces, if they're balanced, they will do this. Right?
If that, what's balanced?
If the pressure force is balanced with the Coriolis force, they will create these motions. So we can look now at the atmosphere and see places where this is true. Because if I see the rotation around an H region, then it must be in geostrophic balance. Does that mean that there is no viscosity there? No. Just means that it's not as important as this balance, right? So this is giving us a tool to identify these things in nature. So if I see something like this, okay, you have a high pressure zone and a low pressure zone. These are contours of pressure, okay? So now you need to make the prediction, you're the meteorologist today, which direction is the flow? By the way, this is us. You live here.
Going this way. Oh, wait. High pressure is gonna wanna come down,
High pressure is gonna go right here, right? Just from
Yeah.
here to here,
low pressure is gonna want to go back up to the left,
just straight, right? Is
yeah.
that true? Or is that opposite of what I've been saying? I don't know. So do these two just connect with a straight line? No, they can't connect with a straight line because the Earth is rotating. So there must be some Coriolis rotation. This is big enough scale, right? That it's important. Of course, it's probably not going to be perfect, but we have some expectation that this should have motion around H instead of from H to L. Which direction do we expect this wind to go? This way or this way?
The right,
Right? Here should rotate this way. Right? Clockwise around H and counterclockwise around L. So I would expect winds to come off of Northern California and winds to go in over Baja California. Okay? Is that true? Bada bing, bada boom. Here's a low pressure system, and it pulls warm, moist air and smashes it into California. Do you remember when we had those like rains, the pineapple rains? Pineapple Express? Ever heard of Pineapple Express? And then not the film. But the film is talking about a meteorologic phenomenon, so it is the film. So the reason that you get that super dank weed in Pineapple Express is because of the abundance of warm air that's being pulled off of the ocean and deposited in Southern California. Okay, that supposedly makes, I don't know if that's true, but that's what people said. Okay. So why does this happen? Why do we have this rotation at all? Because here's the low pressure. They're trying to get to the low pressure, but instead, there's Coriolis force bending them. So they can't make it straight into low. And so you get this rapid. Now, does it complete a nice circle? No. Because that is a first order effect. The circle is the primary shape, and secondary effects, such as viscosity, condensation. I mean, we haven't even talked about the fact that you have multiple phases of media here. You have vapor, you might have ice, right? You have gas. All those things are contributing to the thermodynamics in the fluid. But that second order effect means, okay, yes, you can potentially, like you said, go from high to low. It just might not be in the most straightforward of ways, right? You might spiral out of H and spiral into L. Does that make sense? Okay, here's another example. And this is one of my favorite types of pictures. What is this thing? Yeah. Hurricane. What am I looking at? It's a massive hurricane. Good. Which hemisphere is it in? Or is it in the northern hemisphere? It looks like that picture. Well, that means that you've made an assumption about where the pressure is. You've also made an assumption that this is in geostrophic balance. That the forces here that need to be considered are only Coriolis and pressure. Right? Questions? Where do you think this is? Could this be in the southern hemisphere? What? Wouldn't all the math just be reversed? Wouldn't this just rotate the opposite direction? It doesn't seem right. It doesn't feel good.
Yeah.
Okay. Maybe, maybe not. You don't, I mean, there's no land in the background to help us identify. But what would you have to assume about here? What's in the center?
If that is not in the middle, then that is high pressure, and if it's in the south.
Good. So what you're saying is, based on what looks like rotation this way, spinning, that there must be a high or low pressure in the center. Now, what's in the center of the eye of the hurricane? I didn't include this one here, but let me just freestyle it really quickly. Okay. Let me show you the vertical structure. Oh God, that's really good. Where's the one I want? Where's the one I want? Okay, good. All right. Here we go. In the center, low pressure. Okay. The air actually gets sucked down into the eye. Okay. And what happens is that it moves vertically up, it gets heated up by the bottom of the ocean, rises, and then goes out. Sucked in, rises, goes out. And the bending, the spinning, that's happening like this.
Does it go out because it's like essentially a merry-go-round? That way it causes it to go out, is it spinning?
What do you mean by that?
I'm thinking if at the direct center, you don't see that, at the direct center, you don't see the air being like spun out. But right around, like I say, like the outside of the eye, it starts to go out. Is that because the eye is spinning in like the center of a merry-go-round, but then like as you are not in the center of a merry-go-round, you start to feel the force going out? I don't know if I'm explaining it.
I'm not sure I'm understanding it properly, but let me just show you this, right? So the low pressure is sucking the air down this column. And at the top here, there's actually a high pressure pushing the clouds away. So at the very top of the column, where those clouds form, it's high. And so then it rotates away from it counterclockwise. And at the bottom, it's sucking it in, so the clouds rotate. Clockwise. Assuming that there's vertical stability, right? So there are these like long columns of heated up fluid. So they pull the air along the warm, so this is the ocean. They pull cold air along the ocean toward the low pressure. And as it does that, it heats up. By the time that it heats up, it goes up. So it heats up, it rises, and then it's made this area warm, and so it's too warm, so it pushes the clouds away. Right? So now let's go back to our picture. Let's see if we can understand this. So the problem, of course, is that we're only looking at the top. Okay? Is it rotating this way, or is it rotating that way? Because is it being pushed away, or is it being pulled? It's being pulled only where you can't see it. It's being pulled underneath. Out here, it's being pushed. Right? And at the very top is high pressure. So as it tries to escape, it bends. Yeah, so this is in the middle. Look, it's being pushed out. These tendrils all follow the curve, right? They're not going this way. To get out, you have to push out along these corridors.
I don't know if this is.
This is such a good question, not a dumb question at all. Well, let me ask you this question. How many hurricanes have almost none, or let me ask you a different question. How many hurricanes cross the equator? Yeah, what fuels the hurricane? Hot, cold air, yes. Hurricanes don't happen everywhere. Hurricanes draw not only on the warm air of the ocean, but on the rotation of the earth. They draw and they sap away rotational energy in order to spin up the cloud, right? Because remember, we have to exchange angular momentum with something. Now, it's very marginal. It's very, very small, so we don't notice like the rotation of a hurricane slowing down the earth, but that's what they're doing. So let me show you. This is one of my favorite things to show. Map. This is from NOAA. or no, Earth. Okay, so this is the Earth intensity rotation tracker. It's been around since like the 70s. What do you notice? You think they go this way? Yeah, they all start here and they go this way. But they're rotating this way, counterclockwise. And so as they rotate counterclockwise, they turn and they bounce in and stuff. Sometimes they go like this, bing bong, and that can just depend on what local change. So also, okay. But look how many have crossed the equator. Not a single one. What happens? Let's say you're a drunk hurricane, and you start heading towards the equator. Well, now the Coriolis force starts turning off. Right? And it saps you of all your rotational strength. Because as soon as you cross that equator, you now have to go in the opposite direction. So whatever angular momentum you have, it has to go in the opposite direction. So it has to slow down and stop. By the time you slow down and stop, you're done. Right? You can't start back that way. Look at how drunk this gets. Started over here. Smash back into himself. Right? Why are there so many more in the northern hemisphere than the southern hemisphere? What do you mean? So I told you about two things that hurricanes need in order to be big and devastating. One of them is the rotation of the Earth. The second is the abundance of warm water. So what I'm not showing you here is average sea surface temperatures, nor am I showing you where cold and hot water currents in the ocean are distributed. But let me show you one. So this is an example of the oceanic meridional loop. Okay, so ocean currents are really important. We have these loops that go across the entire planet, and I can actually let me just pull up one. Atlantic. There we go. All right. It's so cool. All right. Here is how here's how the oceans work. Come on. Give me your picture. Show me your picture big. Oh no, it's small. Okay. This is as good as we're gonna get, but I'll just explain what you're seeing. Okay, so this is an example of a meridional overturn. So oceans can obviously sink as they become colder or more saline, and they can rise as they heat up and as they interact with stuff. So basically what happens, let's start down. Let's say you have some nice warm water. You're just gonna travel. You're gonna travel, you're gonna travel, you're gonna travel. You're actually gonna do something really fun. You're gonna come up here towards North America, and you're gonna spend a lot of time in the equator. It's nice and warm, super nice. And you're heating up. And you're bringing with it the fact that it's nice and warm, and it's gonna make all of Europe easy to live in. And then you're basically gonna run into land. And now you need to go somewhere else. And by the time you run into land, most of your heat you gave to Europe, and now you're running into a pretty cold area, so you start sinking. And so this ribbon essentially falls down underneath the circulation pattern, and it heads down through the South America, or down to South America. Yeah, and so it's very cold. And so you haven't quite gotten hot enough by the time that you're here. You have to basically go through this passageway in order to heat up enough to even start one. Right? And on the way back, you're cold. And you're cold, you're cold, you're cold. Sometimes you can go like up here, maybe you turn around the Cape Horn of Africa and you run into the Indian Ocean and you start upwelling. And now it's really nice and warm in the Indian Ocean. So you might get really warm. And so you can get some storms, some tropical cyclones and stuff in this region. I'll show you that map when we go back. But most of this comes back counterclockwise across the whole planet. Okay. And then it goes north. And interestingly enough, in here, you're like, well, there's a lot of hurricanes in there. This doesn't explain it yet. Because you have it has to run here. It's still very cold, runs here into the top of Alaska and comes all the way down. So if you've ever swam in Vancouver or Portland, it is freezing cold. That is this part of the cold subsurface flow, making it to the north and coming back down. Now it starts to heat up. And it heats up a lot, heats up a lot, heats up a lot. And as it heats up, this is now when you start to build your hurricanes. So you get a few of them off the coast here. They mostly go that direction. But now what happens is you have this surface flow that now needs to connect back. So guess what happens? So now this subsurface flow that was cold, it's come to the surface, it's heated up a little bit, like Baja California, Southern California, like San Diego. That's kind of nice, but it's still Florida, right? By the time that you're out here, this is, and by the time that it makes it all the way across the gigantic Pacific Ocean, that is hot water. So you get tons of hurricanes and typhoons in this region. And then you just connect it. And as it goes back down, it starts to cool again. It cools a little bit, not enough to start sinking yet, but certainly enough to not have any energy by the time that you make it back. Hot water, that one. It's hot water. So these are incredibly complex systems, right? Where you can look at any one single perspective and say, oh, that's in geostrophic balance here. But it might not apply to other circumstances because you may need to consider what the rest of the system are doing. Especially when we think about the atmosphere, you can't think about the atmosphere without thinking about what it's on, whether it's on the water, whether it's on land, and how those things are interacting with one another, right? Hurricanes, for example, they happen, well, you can't really see there. They happen here, because you have hot air coming from this direction and cold air coming from this direction, and nothing to block them. If you look across the entire world, okay, mountain range, massive. That blocks the north-south transport. Mountain ranges, north-south transport blocked. Mountain ranges, north-south transport blocked. Mountain ranges, north-south transport blocked. There is no country in the world that has as large and as vast a system that goes from the tropics to the Arctics uninterrupted. Right? You gotta think about the ground. Okay, that was a kind of I went off topic there, but let me show you the maps again. There you go. There's the tropical storm map. You see why it doesn't go here, because the flow comes down. There is another secondary gyre. It's just here. It's like the saddest little ocean current. I can show you all of them, but this one here makes Peru and Chile really, really good fishing. Because what you have is you have a rift and you have an ocean current that's cold and deep and it's beginning to upwell, beginning to come up here, but it's very cold water. So you get almost no hurricanes in the southern hemisphere off of this too. Okay. Reason I got any of this because you should consider something called the Rossby number. Okay, you thought that I wasn't even going to do any class today, but I was just having a good time talking about hurricanes, hurricanes. Okay, so the Rossby number is nonlinear acceleration over the Coriolis. Okay. And really that looks like something And it looks like a comparison here between the advective term, sorry. Yeah, the advective terms, u squared over L times f of u. So this behaves like some speed. So the nonlinear acceleration was u du dx, which looks like u squared over L. Versus the Coriolis acceleration is just, you can say it, it's my favorite one. Fu. Right? So it's like the Coriolis term, or the Coriolis parameter, times some characteristic velocity. Right? And really that kind of looks like, you know, we can cross this one out, cross that one out. It looks like some characteristic. It's so strong. Okay. Over F. Don't laugh. I can be strong. Okay. Over FL. Well, it comes from the top. So I just brought it. But the way that we think about these dimensionless numbers is that they can kind of compare. So here, we have a nonlinear acceleration, which basically acts like your advection number. And so this is a question of which of these two is more important. So if your Coriolis term is large, what is your Rossby number? What's that? Small, very good. So you can type these in. What did we say the typical flow was for an ocean?
Or you're asking.
What's that? Yeah, for the atmosphere, for the wind. How fast does wind blow? 80 years from something. Yeah, 10, 20 is a very good estimation. So let's be a little like less generous. Let's say 10. Okay. The Coriolis parameter, I'll just tell you, is 10 to the minus 4 per second. On average, say mid latitudes. And let's imagine some atmospheric phenomenon being like 1,000 kilometers. So now your Rossby number is like 0.1. So that would be that the Coriolis term is 10 times larger than your advection term. So flow is not being advected, right? It's being bent because you're not moving fast enough compared to how large these scales are and how fast the whole planet is rotating. So that's true certainly for the air. What moves faster? The wind or ocean currents? It's the opposite. So we talked about this, I think it was last Monday, and this sort of people were like counterintuitive. They're like, how slow does the ocean move? The ocean moves somewhere between 10 and 100 times slower than me. Right? Because you're bumping into more things. Right? So if you run around in the air versus you run around the water, you can tell the difference. And the ocean can tell the difference too. So let's look at where the U is. U's in the top. So if this is 10 to 100 times smaller, and we found that over 1,000 kilometers, that the Rossby number was less than 1, what's the Rossby number in the water? It's tiny. So it's tiny. So you're really not affected. Everything is just rotating. And then when you start to look at the ocean circulation patterns, they are just big gyres. They're big rotating circles. And let me show you this too. Sorry, I know that we're running over, but you were late, so I'm going to take your time. Okay. So let me just show you this. If you want to leave, you can leave, but this is cool, I promise. Okay. So these are. This better be big. This better be fucking huge, bro. Oh my God, don't do this towards me. Open in a new tab. Why does it not do that? No, fucking. Open image in a new tab. It always gives you the link. It's like, I don't want to read your article. Okay. So what do you see? Do you see? You see what I see? Circle boys, right? Spinny dudes. Spinny doo, spinny doo, spinny doo. I mean, it's hard because obviously it's the wrong direction here. Goes off and comes back. Spinny doo, different direction. Spinny doo, different direction. Right? And we can follow the path of our friend, the water. Right? So they were very kind. They put cold and warm current instead of that cartoony one from earlier. So you have this current that's cold. It warms up through the equator. It passes through. Right? It goes through. It's getting nice and hot, bounces off of America, goes and heats up all of Europe, gets real cold, comes back down, goes this way, this way, goes that way, goes up that way, goes this way. But they're giant gyres. Right? In the ocean, everything is rotating because of the Coriolis. Now, we haven't talked about vertical versus horizontal rotation, right? Do you think that the rotational speed, do you think the horizontal speed is stronger? We said it differently. Is the horizontal speed greater or smaller than the vertical speed? Horizontal much greater, right? That's what we started with. So a lot of vertical motion is not even happening. So these types of motions here, up and down, right? Those are an even smaller component than the horizontal motion. Good. Okay, is this fun? Does it help you understand the Earth a little bit better? So now you basically understand all of weather. Because you can look at a map and you can say with the highs and the lows, all right, let's do temperature forecast today. No, I know, right? It's very distracting. This is zoom.earth, okay? And here's your pressure map. And you can get this at any time. Zoom.earth, just go a nerd with me. I promise you're gonna love fluids even more. And look at what they have, okay? These are contours of pressure. I wasn't fucking lying, bro. Right? Look at the wind. It goes around the high. And near the high, very low winds. Just in the middle of the high and the low, you're getting, they go through like that, right? But like you said earlier, does it make it from high to low? Yes, certainly. Now, why is that? Well, there's Rocky Mountains in here. These contours are not perfect, right? Let's look at a place where they're a little bit better. Okay, so I can move this. Let's fucking go, boy. Okay, look at that. This thing, it's called the ocean. See how spinny good it is? There's nothing blocking you, right? Now, of course, there's some interaction between the different objects. Look how spinny do that, dude. How does spinny do this, dude? What kind of balance is that? Geostrophic. So geo meaning of the earth, strophic meaning pressure. Okay, not catastrophic, just
What is it?
what? This is a city. Yeah, so like this is Honolulu, the same bridge. It's not telling you the state. It's not saying like not Alaska. It's like saying that wherever. So the cool thing about the Earth is that we have pressure measurements all over, right? So we have like weather stations, and so they can give you updated weather patterns. And when you look at something like this, you can see the whole Earth here, and you can even see here near the equator, you have a phenomenon called the doldrums, where because of the absence of these high and low pressure systems, you can run into an issue where, let's say you are a boat, and you're a boat that you sails around, crossing or going through the equator is quite dangerous. You might run out of air to push you, right? Whereas up here, it's chilling, right? How does your boat go? Well, you follow one of these down, and then you go over with it, and you hope to connect going up, right? You follow them. Cool beans? Sorry, that went long, longer than minutes that, so, okay.